Okay, so in today's class, we're gonna be covering some of the harder questions from our AMC8 practice test the other day. And um, I think these problems will be really insightful, especially for questions 15 through 25. So last week we went through questions 1 through 15 roughly. So this week we're gonna be going over the next set. So go ahead and try this first problem. So it says find the number of factors of 7 factorial times 6 factorial times 5 factorial times 4 factorial times 3 factorial times 2 factorial times 1 factorial. Um, and remember that a factorial, so if I'm talking about 4 factorial, let's say, that means I'm going to be multiplying all the numbers from 1 all the way to this number. So for 4 factorial, I'll be multiplying 1 all the way to 4, so that'll be 24. So go ahead and try this question and type your answers in chat. Okay, so there doesn't seem to be too many answers in chat. I think this might be a bit harder of a problem, so let's go over this one. So first of all, we need to figure out we need to figure out how we can find the number of factors of a number. So let's say we have 24, right? How can we find the number of factors of 24? So there's a couple ways to do this. We can either list out all the factors. So let's do that first, just to get the right answer. So we have 1, 2, 3, 4. 5 doesn't divide 24. We have 6, 8, 12, and 24. So we know there's 1, 2, 3, 4, 5, 6, 7, 8 total factors of 24. So 24 has 8 factors. But how can we find this for any number? Because if our number is in the millions or if it's a really large number, we can't really count all the factors. It'll take too long. So to find all the factors, what you first need to do is take the find the prime factors of the number. So of 24, one prime factor is 2, and 2 times 12 is 24. And of 12, again, 2 is a prime factor, so that leaves us with 6, and 6 is 2 times 3. So we have all the prime factors here, and now we can do the prime factorization. So 24 is 2 cubed times 3. So now we have the prime factorization of 24. How can we get this to become the number of factors? So when we have all these numbers, we notice that 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3, these are all factors of 2. And 3 to the power 0 and 3 to the power 1 are both factors of 24. So right now, we've listed out all the factors of 24 that are some number raised to some other number. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, these will all divide 24. And now what we can do is we need to find every possible factor, and every possible factor is just going to be some combination of these two groups. So as an example, 2 to the power 0 times 3 to the power 0, that's 1. 3 to the power 0 times 3 to the power 0 times 2 to the power 1, that's 1 times 2, that's 2. Then we have 3 to the power 1 times 2 to the power 0. This is going to be 1 times 3, that's 3. Then 2 squared times 3 to the power 0. This is 4 times 1, this is 4. Then 3 to the power 1 times 2 to the power 1. This is 6. And so you see the point. So every possible combination that we take of these two groups, we get one of our factors. So we want to take one value from here, one value from here, multiply those together, and that will equal one of our factors. Does this make sense so far? If you have any questions, please type them in chat. Okay. Okay, so far we know that we need to take one from each of these groups, we need to multiply them, and that'll give us a factor. So we have 4 numbers in this group, and we have 2 numbers in this group. So 4 times 2, that's 8. And so that's how we get our number of factors. And the reason that works is because we take one from each of these, each of this group, and one from each of this group, and if we multiply those together, we find all possible combinations, and so that's all possible combinations equal all possible factors. Okay. If anyone has any questions, please type them in chat. Okay, great. Now, let's try applying this concept to another number. Let's say our number is let's say our number is 18. Go ahead and try to find the number of factors of 18 by using prime factorization instead of by counting them all out. And remember, you just need to multiply together these two groups. So try forming these two groups and find the total number of factors. Okay. I see lots of good answers in chat. Let's go ahead and go over this. So we first want to find the prime factorization. So 2 is a prime number. Let's use that. So 2 times 9 is 18. And 9, we can split that up into 3 and 3. So the prime factorization of 18 is 3 squared. I just took these two threes times 2. Now, to find the number of factors, we need to list our groups out again, something similar to this. So let's list our groups out. We have 3 to the power 0, 3 to the power 1, and 3 to the power 2, and then we have 2 to the power 0, and then 2 to the power 1. So here there's 3 numbers, here there's 2 numbers, and 3 times 2, that's 6. Now, now there's a way to do this even faster. You don't need to list out groups or anything like that. All you need to do is you need to take your prime factorization and take the exponents. So take 2 and take 1, add 1 to each, and then multiply those together. So this is 3 times 2, and that's 6. And this should make sense because here we have 2, and the 2 became a 3 because we included 0. And here we have 2 to the power 1. This 2 to the power 1 led to 2 factors because all we did is count from 0 to 1. So basically, whatever your exponents are, just add 1 to them and then multiply those two numbers together. So even if we look up here, 8 is just 3 plus 1 times 1 plus 1. Okay, so does anyone have any questions? So if there's multiple prime factors, we follow the same method. So let's say our prime factorization is something like 2 squared times 3 times 5. So this is 60, right? Then what we would do is you can think about it as listing out the groups again. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 3 to the power 0, 3 to the power 1, 5 to the power 0, 5 to the power 1. And now all we're doing is we're finding all possible combinations. We need to take one from each group. So we can there's 3 possible choices of taking one from this group, 2 possible choices of taking one from this group, and 2 possible choices of taking one from this group. So 3 times 2 times 2, that is 12. And again, all we did was we added 1 to each of them, each of the exponents, and then we multiplied those together. That's a very good question. Yeah. So this method will work for any number of factors. Because if you think about it, let's say our prime factors are A, B, C, and D, right? And let's say their exponents are just X, Y, Z, W. All we're doing is we're listing out all the possible groupings. So we're going to list out A to the power 0 all the way to A to the power X, B to the power 0 all the way till B to the power Y, C to the power 0 all the way till C to the power Z, and D to the power 0 all the way till D to the power W. And then we count up how many there are. So here there's going to be X plus 1. Here there's going to be Y plus 1. Here there's going to be Z plus 1. And here there's going to be W plus 1. And then we multiply those all together. So it doesn't matter how many groups there are. Um, are there other ways to find the exponent? So for that, you just need to be able to find the prime factors. And for some numbers, it will be really hard to find the prime factors, but it's sort of just, guess and check. So for example, for 18, we know that it ends in it ends in an 8, so 2 must divide 18. So then we split it up into a 2 and a 9, and then we split up the 9 into a 3 and a 3. So you just have to sort of guess and check your way through it. Those were some very good questions. Okay, now let's move on to our problem. Now that we know how to tackle it. So it says find the number of factors of this expression. So the first step is finding the prime factorization of this expression. Let's move to a new page. So we have 7 factorial times 6 factorial, 5 factorial, 4 factorial, 3 factorial, 2 factorial, and 1 factorial. Now, to list out all the exponents, what we can do is we can list them out manually. So we can do 1, and then this is 2 times 1, and then this is 3 times 2 times 1, and keep going. But one really quick way to think about it is our 7 factorial shows up once, so our 7 must show up only once, because 7 won't show up in any of these other factorials, right? For our 6 factorial, it will show up in 6 factorial, and it'll show up in 7 factorial, because 7 factorial is 7 times 6 times 5 factorial, right? And 6 factorial is 6 times 5 factorial. So 6 will show up twice. 5 factorial, similarly, 5 will only show up here, here, and here. So we have 5 cubed. 4, similarly, will only show up here. Let me use a different color. 4 will only show up here, 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 and here. So 4 will only show up 4 times. And we can just keep going. So 3 to the power 5, 2 to the power 6, and 1 to the power 7. So does that make sense what I just did here? All I did was count up how many there are, but I noticed that the 7 will only show up once because 7 factorial is the only number that will have 7 in it. Okay, great. Now we need to find the prime factorization. So one really easy way to mess up this problem would have been just to add up all the add 1 to all these exponents and then multiply them. But this is not the prime factorization because we can split up 6 into 2 and 3, and we can split up 4 into 2 and 2. And we have these exponents as well. So it's 2 squared times 3 squared, and 2 to the power 4 times 2 to the power 4. And now we just add up all our exponents. So 7 times 5 cubed times 3 to the power 5. Oh, sorry about that. So times 3 to the power, we have the 2 here and a 5 here, so that's 7. And then 2 to the power 2 plus 4, that's 10, plus 6, that's 16. So we have these. Now, we take all these exponents, we add 1 to each of them. So we do 1 plus 1, 3 plus 1, 7 plus 1, and 16 plus 1. And this should give you the answer 1088. And we can go ahead and evaluate it as well, just to be sure. So this is 2 times 4 times 8 times 17. So this is 8 times 8, that's 64 times 17. 7 4 is 28, 7 6 42, so that's 44, 64, 8 8 10. So that's 10,088. So I saw a question, why do we need to add one? So going back here, we see that when you list out the groupings, we count from 0 all the way up to our number. And if I was just counting from 1 to n, so if I was counting from 1 to 3, that would be three numbers, right? But if I'm counting from 0 to 3, if I'm counting from 0 to 3, that's four numbers. So when I'm counting from 0 up to a number, I add 1 to that number, and that's how many numbers we have. So when I'm trying to find how large the group is, I need to add 1 to it. And just for demonstration, we can list out the groups. So here, if we list out the groups, we have 7 to the power 0, 7 to the power 1. We have 5 to the power 0, 5 to the power 1, 5 to the power 2, and 5 to the power 3. And then we do the same for 3 and the same for 2. So we see here there's I'll write it on top. So here there's 2 for 7, there's 4 for 5, there's 8 for 3, and there's 17 for 2. And so all we did was we took each exponent and we added 1 to it, right? 1 plus 1 is 2, 3 plus 1 is 4, 7 plus 1 is 8, and 16 plus 1 is 17. Does that make sense? Okay. Okay, great. So that was question number one. Um, it was find the number of factors. So that's a really important concept. So it's good that we learned that today. It's really important to note that that shows up a lot. Next, let's move a little faster so that we can get through as many as we can. Go ahead and try problem number two and type your answer in chat. Okay, so we don't have I want to get through as many problems as possible today. So let's go ahead and go over this one. So it says if the positive difference between the areas of the largest hexagon that can fit in a circle of radius 10 and the largest triangle that can fit in the circle can be expressed as a root b, what is a 10a plus b. So let's draw a quick diagram. So the area of the largest hexagon that can fit in a circle of radius 10. So we have a hexagon, something like that, and the largest triangle that can fit in the circle, so something like this. What is the difference between those? Basically, that's what the question is asking us. Let's redraw our diagram. Um, we have a circle and we have a hexagon in it. Oh, that's not a hexagon. Um, okay, so something like that. So let's first find the area of the hexagon. So in a hexagon, it says the largest hexagon that can fit. From here, we know that the hexagon has to be regular because if all the sides are equal, that'll take up the most area. And sort of intuitively, if you think about it, if I move the hexagon, like if I move this vertex, for example, so if I took this vertex and I shifted it right here, I would be losing out on some area because my height would be max right here. And if you do that for each sort of triangle, you'll see that having a regular hexagon it will maximize your area. So you can sort of use that logic. Now to find the area of the hexagon, we know that the radius is 10, and in an equilateral hexagon or a regular hexagon, all the sides are equal. So all these sides are going to be equal. And a cool property of hexagons, especially when they're regular, or rather only when they're regular, is that you can form equilateral triangles out of all of it. So let's say this is the center of the hexagon. Um, we know that a full circle, so a full circle like this, has 360 degrees in total. So this is 360 degrees. And if we split it up into six equal sections, because a hexagon has six equal sides, each of these would be 60 degrees, right? And what we notice is that these are all equilateral triangles because one 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 arc length basically of a uh like one angle measure of a hexagon is 120 degrees, and we're splitting it in half directly. So this will also be 60 degrees, and this will also be 60 degrees. So what this means is that in that hexagon, especially in only one that's regular, all the side lengths will be equal if you draw a point to the center. And we're in a circle, so this is center. So this is 10, this is 10, and all the angles are equal. So this is an equilateral triangle. So this side length is 10, this side length is 10, and this side length is 10. So to find the area of this hexagon, all we need to do is we need to find the sum of the six areas of these equilateral triangles. And I know this is not a well-drawn hexagon, but let's just say it is. So we have six equilateral triangles, and to find the area of an equilateral triangle with side length 10, the formula is root 3 divided by 4 a square or 10 square. Now this is only one half of the problem, so this is going to be 25, and so that's 150 root 3. So the area of the hexagon is 150 root 3. Now we need to find the area of the circle, or sorry, the area of the triangle. So something like this. So an equilateral triangle, and the problem doesn't specify an equilateral triangle, right? It says largest triangle, but again, we need to notice that if I did move my vertex to a different spot, my area would decrease. It wouldn't be the maximum it possibly could be. So we know this has to be equilateral. So these are all 60 degrees. Now to find the side length, I'm gonna have to use a property of the triangle. So I'm gonna show you two ways to solve this. The first way I'd say is really easy if you know the property. So if I draw a line down the center, this is gonna be the median of the equilateral triangle, and we know the radius. We know from this point to this to right here. We know that this length has to be 10. And what we also know is that this center point is where all the medians intersect, right? Because it's an equilateral triangle and it's inside of a circle. And if we have this length of 10, this length is going to be one half of that. So this is going to be 5. And that's a property of equilateral triangles. We don't have time to derive it today, but you can explore that. I'm sure there's many videos on YouTube for that. But here we have 10 and 5. And so we know that the height of the equilateral triangle has to be 15. And if the height of the equilateral triangle is 15, we can find the area of the equilateral triangle. So we have that this length is 15. And let's just say that this is an equilateral triangle. We know that this is bisected in half. So this is 30 degrees because it's the median of an equilateral triangle. The median of an equilateral triangle is the same as its altitude and the same as its angle bisector because everything is symmetric. And so now we can use our our right triangle formulas. So this is 60 degrees, and so opposite of 60 degrees is root 3. Opposite of 30 degrees is 1, and the hypotenuse is 2. So you're going to need to know something like this. And so this is going to be 15 over root 3. So that's 5 root 3. Yeah, that's 5 root 3. So our side length is 10 root 3. And to find our area, we just do root 3 over 4, 10 root 3 square. So this is root 3 over 4, 100 times 3. So this is 75 root 3. So the area of our triangle, is 75 root 3. So the positive difference between them is 75 root 3 because we do 150 minus 75. 150 minus 75, so 75 root 3. And to find the answer, we do 75 root 3. We do 10 times 75 plus 3, or 753. Now, for using that method, you needed to know a lot of properties of triangles. And those aren't normally taught. So let's go over one more method really quick to solve this question. Um, so we have a triangle like this, right? And we have the center. We know that each of these is 10, and we know this is 120 degrees. So to find the area of this equilateral triangle, we just need to find the area of this triangle, and we need to multiply it by 3. So how we can do that is we have 120 degrees, we have 10, we have 10, and we draw a line down the center, splitting it in half. So this is going to be 60 degrees, this is going to be 60 degrees. And so we know this is a right angle, so we know this is 30 degrees. So opposite of 30 is going to be 1/2 of this because remember right here, opposite of 30 is 1 and the opposite of the 90-degree angle is 2. So opposite of 90-degree angle is 10, then opposite of the 30-degree angle has to be 5. And so this has to be 5√3 because 5 it's 1:1:√3 ratio, so this is 5:5√3 ratio. So then this is 10√3 and this is 5, so we have the height and we have the base. This is 25√3 and times 3, this is going to give us 75√3. So for this, you just needed to know your special right triangles. Okay. Um, so that was question number 2. Let's keep going. So go ahead and try question number 3. Okay, let's go ahead and go over this problem. So it says, let m and n be two positive integers. Which of the following cannot be a remainder of m squared plus n squared? And I see a lot of good answers in chat. So, um, what are the not possible remainders of m squared plus n squared divided by 8? First of all, we need to find all the possible remainders that a square has when divided by 8. So let's just list out all our numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just use the first 10. Now let's square each of these, right? I'll just not write the 2, but let's square them. So 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And now let's find divided by 4 or divided by 8, what is the remainder of all these? So right now we have the square, and now let's find the remainders. So this is 1, this is 4, this is 1, this is 0, this is 24, so that's 1, 32, so that's 4, 48, so that's 1, this is 0. And so we see that it's repeating. It's 1, 4, 1, 0, 1, 4, 1, 0. So now we have all the possible values that m squared or any square divided by 8 can be. So now we can go back to our question. We know that all the possible values are 1, 4, 1, and 0. But obviously, we're just repeating the 1 here, so we don't even need to consider it. So the only possible values are 0, 1, and 4. So which of these can we not form? So we can obviously form 0 just by making both m and n divided by 8 be 0. 1, that's just 1 plus 0. 2 is just 1 plus 1. And 4 is just 4 plus 0. But no matter how hard I try, I can't get 6. 4 plus 1 is 5. 1 plus 1 is 2. 4 plus 4 is 8. So I cannot get 6. So which of the following cannot be the remainder? Our answer is 6. Are there any questions? Okay, great. Go ahead and try problem number 4. Okay, let's go ahead and go over this. So it says 8 people are sitting in a row. Alex wants to sit next to Bob, but not Caroline. How many ways are there to arrange the people? What I like to do for problems like these is first sort of draw a diagram. So let's say we have 8 spots. And let's say I place Alice right here, or let's just refer to them as A, B, and C, just for convenience, right? So A wants to be next to B, but not C. So let's say I place A here, and let's say I place B right here. Then I cannot place C right here. I can only place it in one of these spots. The problem arises, however, for us when Alice sits in one of the edge corners or in one of the edges. Sorry. So if Alice sits here, or if Alice sits here, uh, B can only sit here, and so C has to sit in one of the other spots. So when we're counting, we need to account for this. And so the easiest way to do this is to form two separate cases. So in this case, so let's do case number one right here. So there's 6 spots for Alice. So there's 6 spots. 1, 2, 3, 4, 5, 6. There's 6 places for Alice to be. And for B to go, for Bob to go, you have two choices. You can put Bob in one of the spots next to Alice. So you have 2 choices for Bob. And for C, so that's Caroline, you cannot choose this square. So you need to choose one of the other 5 spots. So this is for Bob, and then this is for Caroline. And now we have 5 other people still, right? Because I let's say I remove this square, then I still have 1, 2, 3, 4, 5 other people. And so that is 5 factorial because I can arrange them in 5 factorial ways. I can choose 5 people to be here. I can choose 4 people to be here. I can choose 3 people to be here, 2 people to be here, and one person to be here. So that will account for all our cases. And so this is going to be 6 times 5 factorial. That's 6 factorial times 10. This is going to be 7,200. So this is only one of our cases. Our other case is if Alice is on the edge, in which case there's 2 possible ways. Alice can be on this edge or Alice can be on this edge. For Bob, there's only one possible spot. And for the rest of the people, it's just 6 factorial because it doesn't matter where Charlie goes. Or, sorry, Caroline goes. It doesn't matter where C goes. Um, they can go in any order they want. So I have 6 ways to choose the person that goes here, 5 ways to choose the person that goes here, 4 here, 3 here, 2 here, and 1 here. So this is 6 factorial times 2. That's 1440. Oh, or sorry. That's 720 times 2. Yeah, no, sorry. That is 1440. So 7,200 plus 1440. That's going to be 8640. And our final answer is 8640. Okay. Um, is there another way? So factorials is I mean, I'm pretty sure that's the only way. There might be another way, but how you can think of this is think of using 6, 5, 4, 3, 2, 1, and then you just need to multiply them all together. Factorials is the most straightforward way. Okay. So I know we're going through these pretty quickly, but I will make the recording available so you can rewatch it if you need to. Let's go ahead and go over number 5. Go ahead and try this and type your answer in chat. Okay. Let's go ahead and go over this one. So I do think this one was a quite challenging one. It took me like a minute to solve when I first saw it, but let's go ahead and go over it. Um, so x minus y square plus y square. This is an integer, and let's say the integer for our sake is just m, right? And xy is a perfect square. What is the value of root xy? So first, let's expand everything. So x squared minus 2xy plus y squared plus y squared, so that's 2y squared, is equal to m, which is an integer. And we're also given this. So x to the power 4 plus 4y to the power 4 is equal to 65. And we see these values here. So x squared plus 2y squared. And we notice that squaring them will give us something similar to this. So we're just going to go ahead and move 2xy to the other side. So then we're left with x squared plus 2y squared is equal to m plus 2xy. And then we'll square both sides. Because we see that squaring x squared will give us x to the power 4, and squaring 2y squared will give us 4y to the power 4. So then we'll evaluate these. So we get x to the 4 plus 4y to the 4 plus 4x squared y squared. This is equal to m squared plus 4mxy plus 4x squared y squared. So then we cancel out 4x squared y squared, and we're left with x to the 4th plus 4y to the power 4. So that's 65. This is equal to m squared plus 4mxy. And now we are told that xy is a perfect square, what is the value of square root of xy? We can just test some values, and if we test 1, we'll see that xy needs to be 16. And so our final answer is 4. So I know it can be very hard to solve problems like these because you sort of just need mathematical intuition, but that comes with practice. So just keep doing more problems that are similar to this, and you should be able to solve them. Um, and again, I know we're moving pretty quickly through them, but I do want to get through as many as possible. Um, okay, so let's go ahead and go over number 6. This is very similar to the Monty Hall problem, but for 5 problems. So go ahead and try it. Okay, let's go ahead and go over these. So John is shown 5 boxes and told that one of them contains a prize and the rest of them are empty. He is told to choose one of the boxes. Then one of the empty boxes is removed. John has the option to open his chosen box or switch and open another box. Assuming he uses an optimal strategy, what is the expected number of prizes that he will win? So, just to clarify, expected number of prizes is basically what is given our probability, and let's say he uses the optimal strategy, what do we think he's going to win? So this is just like the Monty Hall problem, but for 5 boxes, and we need to figure out what the optimal strategy is. So let's draw a small diagram. Let's say the prize is right here. John has a 1/5 probability of getting the prize on his first turn, basically, and he just needs to stay there, right? So 1/5 times 1, so that's 1/5. Now, if he doesn't, if he lands on the wrong box, so he has a 4/5 chance of landing on the wrong box. So let's say he just picks this one, and the judge or whoever removes the boxes will remove one box, and we're left with 3 boxes. If he decides to switch, which he pretty much has to, right? Because we know that his box right now that doesn't have the prize in it, so he is going to switch. But when he switches, there's only a 1/3 chance of him switching to the right box. So 4/5 times 1/3, that is 4/15. And 1/5, this is 3/15. So we know 4/15 is greater than 3/15. So the optimal strategy is for him to switch the box. So now we will calculate expected value. Our expected number of prizes is just going to be our probability times the number of times we play. So this is 3, and 3 times 4 is 12. So our answer is A. Okay, let's go ahead and go over problem number 7. So the question states that Joey has a calculator that can add or subtract. So it has these keys, and he randomly spams 3 keys and he presses enter. His calculator gives a syntax error if it sees 2 sign operators in a row or a sign operator at the beginning or end of an expression. So just to sort of give some context, if you see a negative here and then you see a number, this would not count as a positive as a case. So just to give a bit of context, let's say you have negative and then 79. This would give a syntax error. If we have something like that, that would give a syntax error. So basically, anything where the sign is not in the middle, it would give a syntax error. Now, assuming that a syntax error has a value of -1, what is the expected value that Joy's calculator will output? So there's 3 possible cases in this problem. One case is where the middle is a positive. The second case is where the middle is a negative. And the third case is where there is no sign. So it's just a number. So like 1, 2, 3 or something like that. So we need to do all the possible cases. So let's first go over this case. So we'll call this case number 1, we'll call this case number 2, and case number 3. For case number 1, we need to find all the possible sums and we need to add those together. So here we have 1 through 9. We have a plus and we have 1 through 9 again. So we need to find all possible sums. So let's go ahead and list these out. Now, when I add them, I'll be adding every possible combination of 1 with each of these, and I'll be adding those numbers together. So 1 plus 1 plus 1 plus 2 plus 1 plus 3, all the way to a plus 1 plus 9. Now I'll have 9 ones, so 9 times 1 plus I'll have 1 through 1 plus all the numbers till 9. To calculate this, we're going to use our triangular numbers formula. So whenever you have a number and you're trying to add up 1 all the way till some number n, the formula is just n times n plus 1 divided by 2. So we're going to use that formula. And so we have 9 times 9 plus 1 divided by 2. So this is 9 times 10 divided by 2. This is 5. So this is 9 times 1 plus 9 times 5, that's 45. And so this is the sum of all the possible cases if 1, so this is the sum of all possible cases if 1 is right here. We have to do the same thing if 2 is right there, 3 is right there, all the way until 9 is right there. So just to do that, the only numbers that's going to change is this right here. So it's just going to be 9 times 2 plus 45, 9 times 3 plus 45, all the way to 9 times 9 plus 45. And that's because the only number we're really changing is this number right here. We're going to be changing that to whatever this number right here is. So let's say we're on case number 2. This number would be swapped with 2 in all possible cases. But the 1, 2, 3, all the way until 9 would stay the same. So now all we have to do to get our first case answer is add all these up. So there's 9 cases total here. If we count all these up, you'll get 9. So this is 45 times 9. And to add all these up, I'll just factor out 9. And I'll add up 1 all the way until 9. So this is 9 times 45 plus 45 times 9. This is just 9 times 90 because I factor out the 9. And so this is 810. Okay, so that was a lot of 9s. So I suggest working through that yourself to sort of understand what happened. Okay, so now for case number 2, this is a subtraction case. So we have the numbers 1 through 9 here. We have minus, and then again the numbers 1 through 9. And there's I really like this case because if we list out all the numbers, right, we'll see a bit of a pattern. So I'll add up again all the numbers, or rather subtract up all the numbers. So it'll be 1 minus 1 plus 1 minus 2 all the way to 1 minus 9. And I'll do the same thing for all the numbers. So 2 minus 1 plus 2 minus 2 all the way until 2 minus 9. And I'll keep doing that until 9 minus 1 plus 9 minus 2 all the way until 9 minus 9. And we notice a bit of a unique pattern. So this 9 shows up 9 times, right? Because I'm going to be doing this for 9 separate cases. So this 9 will show up 9 times. But so will this 9 show up 9 times, right? Because there's, again, 9 numbers right here. So there's 9 plus 9s, and there's 9 minus 9s. So this is just going to be 0. And we notice that's true for every possible case. So let's do -2, right? -2, -2, -2 right here. And that's just going to keep happening 9 times. So we have 9 times -2. But for +2, we again have that 9 times as well, right? So 9 times +2. So this is just going to be 0. And so we can do that for every possible number. And we get that case 2, our answer is just 0. So this is just 0. And now for case 3. So case 3 is when it's just a number. This one's a bit tricky. So let's write our 3 placeholders. We can have any number 1 through 9, any number 1 through 9, and any number 1 through 9. How we do this is you can think of the number 123 just as an example, right? This is 100 times 1 plus 10 times 2 plus 1 times 3. And so we can use these same placeholder values here as well. So we can do 100 times whatever number, right? Plus 10 times whatever number plus 1 times whatever number. So the numbers 1 through 9, they will repeat 81 times. So the whatever's in the unit digit, it will repeat 81 times because this case is 9 times 9. So whatever number is here will repeat 81 times. In other words, when we're adding up the number, we need to do 81 times what all the possible values are. So all the possible values, there's going to be 1, 2, 3, all the way until 9. These are all the possible values. and each one is going to repeat 81 times. So if each one is going to repeat 81 times, we can do is we can factor out the 89. Or if each one is going to repeat 81 times, we can factor out the 81. And so this is going to be 81 times 45. And the same is going to be true for each placeholder, right? So what we can do is we can write 81 times 45 here and 81 times 45 here. And so we can factor out the 81 times 45, and this will be 111. And now we just need to evaluate this. So this is going to be, or rather, actually, we do not need to evaluate it, but we do need to evaluate it in the end, but we can make it simpler by first adding our 810 first. So this is 8 plus 810. So this is the total sum. And then we need to subtract some cases, right? Because there are some possible values where we'll get a syntax error, and that's a value of -1. So right here, this had 9 times 9 possible cases. This had 9 times 9 possible cases, and this has 9 times 9 times 9 possible cases, right? So this is going to be 162 plus 729. This is going to be 891. And we have a total of 1,331 cases, right? Because we have the 9 digits plus the two placeholder plus the two add or subtract values. So that's 11 total possible values that we can put in each spot. So this is going to be 1331. And we subtract with 891 because 891 values are valid. The rest will be syntax errors. So this is 0. We'll put a 2 here. This is 4. This is 440. So we get 440. We need to subtract that. And in the end, we need to divide by 1331 because it's asking us for expected value. And so we need to divide it by our remainder. Or we need to divide it by our total number of cases. And so now the hard part is just evaluating this. So we factor out 81. So this is 45 times 111. So when you evaluate that, that's 4995 plus 10 minus 440 divided by 1331. So this is 5005, right? Yeah, sorry. And it's times 81 minus 440 divided by 1331. So then this is 5 times 81 times 1001 minus 440 divided by 1331. And so this is 5, this is 405. And we can use our 1001 trick. So this is going to be 405 minus 440. So if we evaluate that, this is going to be 0, this is going to be 3, this is going to be 10, this is going to be 6, 9, so 404, 960. Oh, I accidentally did this one wrong. So 404, 965 divided by 1331. And that's our final answer. So 404, 965 over 1331. And lastly, we have problem number 8. This is a nice problem because it demonstrates a key concept that's used in competitive math, and that's stars and bars, sticks and stones, whatever you like to call it. It says Alice has 24 apples. In how many ways can she share them with Becky and Chris so that each of the 3 people has at least 2 apples? So we have 24 apples, and we have 3 people. And we have 3 people. And we want to give them 2 apples each at the very least. Okay, so let's go ahead and assign 2 apples to each of our 3 people. So this will be 6 apples total we're taking away. And so this is going to leave us with 18 apples to divide among these 3 people. So we can draw our 18 apples. And we can draw 2 dividers, basically. Because to divide our apples into 3 groups, we need 2 dividers. So as an example, let's say we place our both our dividers right here. We're given 2, 4, and then the 12. So 2 apples will go here, 4 apples will go here, 12 apples will go here to A, B, and C respectively. And so this will account for all our cases. So now all we need to do is we need to find how many ways are there for me to put the dividers down so that we can divide up the apples. And how we can think about this is that we have 18 apples and we have two dividers. And I need to find out how many ways there are to arrange them. So if you think about it, to arrange any object, so let's say we have a bunch of apples, oranges, and bananas. Then there's three fruits I can choose here. And let's say I can't repeat a fruit, right? So there's three fruits I can choose here, two fruits I can choose here, one fruit I can choose here. So this is six. So if we use that same logic here, in the first spot, I have 20 total items. So there's 20 things I can put here. In the second spot, I have 19. In the third spot, I have 18, and so on, all the way to the last spot where I only have one. So there's 20 ways. So there's 20 total things, and there's 20 factorial ways in which I can put them all down. However, all the apples are the exact same. So this, for example, let's say let's just say we have three apples. If we counted these as 3 factorial, so if we counted this as 6, this would be saying there's 6 possible ways for me to put the 3 apples down, even though it would just be looking like this, right? All 6 would just be looking like this. It would just be looking like 3 apples sitting next to each other. But how we counted it was that there's 3, 2, 1. There's 3 possible apples I can put here, 2 possible apples I can put here, and 1 possible apple I can put here. And so we're saying there's 6, but all the apples are the exact same. So to us, it looks the same, and the case itself is the exact same. So I can't just use factorial each time. What I need to do after taking the factorial is I need to divide by all the possible ways in which the apples can be arranged. So in this case, the apples can be arranged in 3 factorial ways. So to put these down, I'm going to take the total possible value and divide it by all the ways in which the apple can be put down. So that will give us one total case. So there's one case total. So how you can think about this is in our problem, I'm going to divide by 18 factorial for all the apples and 2 factorial for the dividers. And the reason being, so let's go back to the example where I placed my apples here and here, I think, or it was something like that. It doesn't matter. What I'm doing by dividing by 18 factorial and by dividing by 2 factorial, I'm basically saying it doesn't matter. I'm going to divide by 2 so that even if my test cases say that I swapped these two, I'm dividing by 2 to account for that. And for the apples, right? This counting by doing 20 factorial, what I basically said was, let's say I put my dividers here, there's 18 factorial ways in which I can move my apples around, right? So this same case is going to be counted 18 factorial times because when my dividers are here, my apples can be moved around in 18 factorial possible ways. Because there's 18 apples I can put here, 17 I can put here, all the way until one apple I can put here. So by dividing by 18 factorial, I'm removing all those cases. And by dividing by 2 factorial, I'm removing all the divider cases. So this is 19 times 20, and this is 10, and this is 190 total. So let's go back to our problem. In how many ways can she share them with Bobby and Chris so that each of the 3 people has at least 2 apples? Our answer is 190. So this was an explanation for stars and bars. If this did not make sense to you, there's so many more resources online that teach this concept very well, much better than I can. So I suggest you go take a look at them if you're still confused. Thank you for watching.